Thank you very much. I'm really pleased to be invited. It's a wonderful conference. It's a pleasure to be able to see names that are not familiar, but I know in many years will be the famous people in our field, and I've known them before anyone else. Okay, so this was an interesting invitation. I'm not an information theorist or a communications person, but I certainly have a lot of interest in it, and I have some recent work that has that flavor, and I thought, well, great opportunity. I'll talk about divergences and relationships and statistics and everything. But I decided at the end of the day not to give that talk. I think that what I'm going to talk about is more inference as some of the directions I feel are very important for the field of inference. And I think especially for younger people, this is an area that you're going to want to know about as time goes on. So, classically, a lot of the fields that we're all interested in were kind of broken up into little fiefdoms. 40 or 50 years ago, they weren't. People like Kolmogorov and von Neumann and so on and so forth had a unified view of information and computation and statistics and inference and so on. But the problems, I guess, were just so hard that people after that had to kind of start break them up. So in lots of information theory courses, you will see all kinds of probabilities all over the place, but you'll rarely actually see much about inference. And by inference, I mean I have data, and I want to get some knowledge out of that, often in the form of a probability distribution. So where do those probability distributions come from? And, it's amazing how much information that you can do without ever actually asking that question. Your channel is assumed known. Well, what if it's not known? And so on. And signal processing, similarly. I took lots of courses in signal processing. It's a great subject. But generally, it was just about processing signals. It wasn't about doing inference, taking data in, and then saying something about some knowledge that you got out of that data. You assume. More recently, I got interested in distributed detection for various reasons. I think it's a great problem. I know several of you work on it. So we read all the literature, wonderful literature. All of it assumed that all the probabilities were known. And the problem was just how to integrate signals. Okay, so there was a missing kind of, there's a gap there. And then recently, in the fall, I was at MIT for a big workshop on control theory and information and communications and so on. And it occurred to me that many of the great EE departments in the world are at places where there's no stat department. So there's EE at MIT. There's no stat department there. Caltech similarly, Princeton similarly. Now there are some exceptions here. There's a stat tradition. Berkeley and Stanford have them, but it's pretty amazing. So I think this gap is really unfortunate. And so part of the talk here is to try to bridge the gap a little bit. So instead of by doing it a little bit, I've decided to kind of go whole hog and go on into an area of Bayesian nonparametrics, which is one of the kind of more exotic areas of statistics, but it really brings up some inferential issues that I think you're going to be interested in. And they have interesting ties to stochastic processes and to combinatorics, which are other areas that are in the spectrum of applied math that I think some of you will be interested to know about, and maybe this will intrigue you. So I doubt you'll understand all of this talk. I doubt you even understand the title. And so the goal is just to kind of open the window a little bit and show you some of these ideas. Maybe you'll find something interesting. Maybe you'll want to follow them up. You're young enough that if you want to follow them up in a year or two, your brains would soak them up like sponges, I think. So before jumping into that, I do have a slide on some alternative talks I might have given. This is just shameless publicity. So I've been working with my colleagues, mainly Xuanlong Nguyen, who's now at Michigan, and Martin Wainwright at Berkeley, and Guillaume Obozinski is in France, on several papers on divergence functionals, likelihood ratios, convex risk minimization, and so on. That would have been pretty natural, more natural to this audience, but I just put them up there for shameless publicity. The first two are on really Chishar and F divergences and how they relate to statistical issues, in particular what are called surrogate loss functions. And then the third paper is on kind of the timely topic of L1 and group L1 regularized regression. Okay, so I'm not going to talk about that. What I'm going to instead talk about is Bayesian nonparametrics. Okay, so why be Bayesian? Well, I'm giving a talk. I'm giving a lecture series on that at Berkeley right this moment. There's lots of reasons to be Bayesian, mainly because Bayesian inference methods have good frequentist properties, so it kind of helps unify statistics to approach problems with a Bayesian point of view and then analyze them with a frequentist point of view. But maybe for this audience, a good way to say it is that Bayes does have the virtues that allows you to assume partial knowledge of probability distributions, or even full knowledge of probability distributions in the form of prior distributions. And since, like I was alluding to, a lot of information theory assumes you already know the whole probability distribution, it's not so uncomfortable to be a Bayesian from that point of view. So that's kind of one way of arguing it. Now, non-parametrics here, in most of the statistics, non-parametric just means not parametric. In Bayesian statistics, non-parametric has a sort of more precise meaning. It means that the prior is not just the prior is a stochastic process. So remember what a stochastic process is. It's an indexed collection of random variables. If the index set is infinite dimensional, that's the more typical stochastic process, and that's what we mean by Bayesian non-parametric. Actually, it's not that there aren't parameters. It means there's an infinite number of parameters. Kind of a bad terminology in a way, but there you have it. All right, so in classical Bayesian analysis, if you open up a text, you'll see a formula like that, and that clipped in from, that's where I'm going tomorrow, Friday, and I don't know how it got into my talk, but it has, that's an address of a place on University of Illinois campus in Chicago, so there you go. Has nothing to do with Bayes' theorem that I'm aware of. Anyway, there's Bayes' theorem that the posterior is proportional to a likelihood in a prior. And theta here is generally thought of as a finite dimensional vector, a Euclidean vector. And the prior on that is just a classical distribution, exponential family typically. But really, a lot of Bayesian work and theory goes through for theta being an index on a bigger space, not an Euclidean space, maybe on a function space, a Banach space, a measure space even. So theta can range over a big class of objects, and you can still do Bayesian analysis. So when that happens, we usually don't write theta anymore. We write g, just to make clear that we're doing something a little more exotic. And so conditioning on g, and you'll see a lot of examples of g. G could be a tree of arbitrary depth and branching factor. So it could be discrete but countably infinite. Okay? And conditioning on it, then we'll talk about the probability of the data. And so this object is not so exotic at all. So lots of geneticists work with trees of infinite depth and breadth, and this is just the mutation process on the tree or something. So, there's tons of examples of these sort of things. Here's a little more exotic. G is now an infinite object. We have to talk about a probability distribution on G. And that's a stochastic process. Okay, now actually the math doesn't, this is not quite right. In some sense, the posterior should still be proportional to the likelihood times the prior. There isn't really a Bayes theorem like this for general stochastic processes, so that's kind of a misleading equation, but the spirit is true. That we just replace the prior distribution with a stochastic process, multiply that by a likelihood, and then in some sense updated that into a posterior. So after you've seen data, what is your new probability distribution on the class of infinite object that you might be interested in? Okay, so what kind of classes of G are we interested in? Well, here's a bunch of them that I've been working on recently, and there's a field of a couple hundred people who call themselves Bayesian non-parametricians who work on these things. So directed trees of unbounded depth and unbounded fan-out. There's lots of applications of that in document processing, in image processing, in genetics, and in many other fields. Partitions, well, that's just another way of talking about clusterings, but where you often don't know the number of clusterings a priori. So we talk about arbitrary partitionings on data points. As you get more and more data, you get more and more partitionings. We want probability distributions on those objects so we can then do inference. Sparsity is all over the place. We can talk about probability distributions on sparse binary infinite dimensional matrices, and there's a whole bunch of others. And as you start to get further and further down here, you can talk about distributions on distributions. And you sort of get a recursivity that's very natural in Bayesian analysis, and you'll see examples of that. All right, now things can start to get intractable as you start to go down these hierarchies, and you kind of have to worry about that. And so a tool I'm going to propose today is something called a completely random process, or really a completely random measure. And I'll define that here pretty quickly, but it has a nice kind of divide and conquer property to it that allows computational machinery that's pretty efficient to be applied to these ideas. All right, so that's kind of one class of ideas, we'll get to completely random measures here in a minute. Another kind of cut through the space is that we want to build big models out of small pieces, and the main way that's done in Bayesian analysis is what's called hierarchical modeling. And if you pick up a Bayesian book, this is one of the first things you see, is that you have a prior distribution of some kind. It has its own parameters, and you have to put up a distribution on that, and it has its own parameters, and you keep going up. And that's a good thing, because it often allows you then to tie together things. So I can have a distribution over here with a parameter mu, another one over here that has the same parameter mu, and I can say mu comes from some distribution. I've just suddenly tied my two parameters over here. And in systems with hundreds of thousands of parameters that we often work on, you better do that, because otherwise you have too many parameters and you start to overfit your data. So Bayes is a really good way to control overfitting. So in this non-parametric setting, the same kind of idea goes. We have a stochastic process that has a parameter that may be itself a stochastic process. And we've been tied stochastic processes in this way, very natural. Less traditional, but equally important, is something called nesting, where you pick one or another of priors or stochastic processes. So this is often thought of as a mixture model or maybe a countably infinite mixture model, and we'll see examples of this. So both of these have both statistical and computational justification. Hierarchy is kind of like recursion from a computational point of view, and nesting is really like divide and conquer. And then statistical rationale for both of them as well. All right, so let's just jump on the other. Let's talk a little bit about some practical applications of these kind of ideas. I don't want to just give the impression this is a mathy presentation with no impact on the real world. Here's a problem we worked on. We, in this case, being with Emily Fox, who's a student in LIDS at MIT. Speaker diarization. You have one microphone, a bunch of people around the room, and you want to find who's talking and when. Okay, so that's the gold standard. You want to induce that, infer that, and here's your data. So it's just one microphone. So it's kind of has a favor of a change point detection problem. You want to figure out when a change occurs, but that's not really the right way to think about it. Because you notice, for example, that Bob speaks here, and then Bob speaks again. Okay, so this change point here should use some information about what you learned from Bob back in the past. Right? And most change point detection doesn't do that. So it's kind of more of a state space Markovian flavor, where the state is some object that's has to do with the speakers. Now there's an unknown number of speakers in the room, so the state can't be a fixed dimensional finite vector that you know the state space dimensionality a priori. Okay, so that already suggests we might want to be using non-parametric ideas where the state space can be open-ended and potentially infinite. Okay, here's another applied problem that I'm going to talk about. So this is motion capture analysis. This is from CMU. So these guys just did motion capture on people doing exercise routines. So someone would do a few seconds of jumping jacks, then they would run in place, then they would twist or squat or whatever. That's one particular person. So we get a time series, multivariate time series for one person. Then we have another person doing another set of exercise routines, and there's a multivariate time series for them. So we have a collection of multivariate time series. And we know nothing. That's our data. And we'd like to infer some aspects of this, that we'd like to learn that there are jumping jacks in the world, and twists, and crouches, and so on. And so we need to have some notion of a hierarchy here, because if one person does jumping jacks, that should help us to figure out that jumping jacks is happening in a different video as well. So we want to shrink or share information across multiple time series. So this really, to me, again, suggests non-parametric kind of thinking. I wouldn't know how to parameterize this sort of space, and I wouldn't know how to, I have too many arbitrary decisions about how many kinds of exercises there are and how many kind of clusterings and so on. So non-parametrics is going to be useful here. Okay, so I will return to those problems and show solutions to these, which are state-of-the-art. In particular, in speaker diarization, we have the world's best results on that particular data set. So what is a completely random measure? Now to go back into the math. So it's a very natural definition. It's the following. So a measure, of course, is just it's a measure. There's a measure space, and for any subset in the measure space, it assigns a number, the measure of that subset. And a random measure just does that randomly. So if you pick out a set A, a subset A, all right, then I draw a random measure from in a way I'll be talking about, and that will then assign measure to the set A. Let's call that G of A. So G is the random measure. G of A then is a measure of set A. That's a random number now, a random variable. Okay? If I keep drawing different G's, I'll get G of A will be a random variable. And if that's true for every set A, I've got now a collection of random variables. That's a stochastic process. Its index set is the set of subsets of a space, i.e. a sigma algebra. Okay? So that's kind of that's the definition of a random measure. Now, completely random measures, is due to Kingman, is really simple. It just says that if I have a set A here and a set B here, G of A and G of B are independent random variables if A and B are disjoint sets. Okay, extremely natural definition. Okay, it doesn't have to always be the case. There are many other examples that aren't completely random, but this is a very broad class of random measures. And it leads to, as I was saying before, sort of divide and conquer. What happens over here is independent of what happens over here. My computational machinery can work on them separately. So Brownian motion is an example of this in one dimension or multiple dimensions, right? You know about independent increments processes, probably. This is a generalization of that to arbitrary spaces, not just to the real line or to Euclidean space. Gamma processes, I'll talk about a little bit, beta processes, and compound clone processes are all examples of this. They turn out to be discrete with probability 1. That's an important fact due to Kingman. So I'm going to be drawing completely random measures, and they're kind of little spiky diagrams, where the locations of the spikes and the heights of the spikes are both random. All right, now these are random measures. They're not necessarily probability measures. They don't necessarily integrate to 1, and that's actually a big, important virtue for us, that we don't want to restrict ourselves to probability measures. Here's a picture of one. So the red object there is a specific measure. It's on a set omega. So if I look at any set A and any set B, there's a certain amount of mass that falls into that. That is the measure of those sets. Okay? And if these measures assigned to here and here are independent, then I have a completely random measure. Okay? So that's a measure, and a random measure just is a kind of there's an ensemble of such objects. Now, you can get all of them. There's a characterization of completely random measures in the following way. So this is an important slide. Let me take a minute to do this pretty well. Okay, so here's our original space omega, and I drew that as the real line just so I could make a picture, but you should think of that as an arbitrary space, even a function space, in fact. Think of it as a really general space. We're going to now take the cross of that and the real line. Okay, so we're going to work on omega cross R. On that space, we're going to put a surface, okay, which is going to be called a rate function. Okay, it's a product measure. Okay, so that defines a rate function, and we're going to use that as a rate function for a Poisson process. So you all know what a Poisson process is in kind of the classical case of the real line. Every little interval has a Poisson number of points falling in it, okay, and they're independent of two different intervals. It's a completely random measure. It's a simple example of that, right? In the classical case, the rate measure was just constant. You had a constant rate for the Poisson in every little subset. But an easy generalization is just to allow the rate to be variable. So I have a rate function for the real line. Now just generalize that to an arbitrary space. I have a rate function, which is an arbitrary function, and I integrate over some little region, and I get a number, and that goes as a rate into a Poisson distribution. And I get a Poisson number of points for that. So I've done that. I've sampled from this rate measure. It's a non-homogeneous Poisson process, and I get some points in the plane, in this case, these red things. Okay? Now, take each one of those points and drop it to the omega axis. Okay? And you get these sticks, right? These discrete atoms. They have certain locations, and they have certain heights. And then erase the diagram and treat this object here as that object G. It's a measure on omega. So we use this real line just to get an augmented space. We did a non-homogeneous Poisson, and we threw all that away, and we got ourselves a measure on omega. All right, that is due to Kingman. Kingman in '68 showed that that characterizes all of the completed random measures. That's the way you can get all of them. Pretty important result. If this rate measure integrates to a finite value over all of omega cross R, then you get a finite number of points here. But we're not going to be interested in that. We're going to be interested in non-parametric. So we get this rate measure to go off to infinity and integrate to infinity. And when that happens, you get a countable infinite number of points. And that's what we want. That's going to give us a countably infinite number of parameters in our prior. Here's an example of such a countably infinite setup. This is an important process that I'm going to argue gives you sparse binary matrices. So you should be interested in this for all kinds of reasons. It's already being used now, in fact, for some kind of image processing with sparsity sort of story. This is called the beta process. So the beta process, remember we have two arguments, the omega cross R. So to talk about a rate function, we need two arguments, omega and let's use P to index the real part of it. So this is a measure. It has two parts to it. One of them is just a measure on omega space, and that's just an arbitrary measure. I'm calling it B naught. Okay, so I had it be uniform in previous, but you can make it be anything you want. It kind of gives you where the points are located, where the atoms are located. Right, more importantly is this part of it, and I'm not writing this as a density. Okay, it's a density. And this part of the density looks like a beta density. Okay, P times 1 minus P to some powers, that's called the beta density. All right? This beta density has, normally you would have an alpha 1 here, and an alpha 1 would be strictly bigger than 0. Alpha 1 here is 0. So this means this actual is a degenerate case of the beta density that integrates to infinity. Okay? So if you use this as your rate measure for a Poisson process, you will get an infinite collection of points in the plane. All right? And the construction I had on the previous slide we written out mathematically as follows. Sampling from the Poisson process with this as the rate measure, you get a collection of points, omega I, pi. Those are those red squares, red things in the plane. Take the omega I and make them be atoms. Okay, and their heights are given by pi. So that's just that construction where I drop things to the omega axis. And there's an infinite sum here, and that object now is a random measure. Okay, hopefully that's clear. So that's one example of a process that I hope you'll be interested in. Another one is where instead of using the beta distribution on the real values, which actually is concentrated on 0, 1, the beta, you can use the gamma distribution and make it be a improper gamma that integrates to infinity. All right, now you're going to get a bunch of points that don't live on 0, 1 anymore. They live on 0 to infinity. And again, it's going to be, most of them are going to be small, but there's going to be a countably infinite number of those guys. And that object now is called the gamma process. Okay? And there's another object which is even more famous called the Dirichlet process. And the Dirichlet process is just gotten by taking the gamma process and normalizing it so that it actually it integrates to 1 across the omega space. Okay? The Dirichlet process is not a completely random process. By normalizing, we've coupled variables. If something's big over here, it has to be small over here, so that total is 1. So it can't be completely random, but it's almost completely random. All right. So hopefully that's not an unclear kind of set of ideas. All right. Let me shift gears now a little bit and start to put this into some machinery that you're more familiar with. We now have a tool, all right? Just like you had the Gaussian distribution and the multinomial in your toolbox before, you now have a new tool where you can construct more rich classes of distributions. And now you can start putting those distributions in places that you might not have think of putting them in before. So let's put them in hidden Markov models. And what we're going to do with this is going to solve what's been kind of an open problem is hidden Markov models where the dimension of the state space is unknown a priori, unbounded. Okay, so just this is a picture to remind you what HMMs are. How many of you know what an HMM is already? I suppose most of this audience. Good fraction of it. Okay, I'll go quickly. Hidden Markov model, there's many diagrams of this. This is a graphical model, my favorite one. You have it's a doubly stochastic Markov chain. Here's a Markov chain up here, which is unobserved. That's the no shading. And then hanging off of that, you have the observations. They're shaded, so this is stochastic, and the transition matrix is stochastic. The transition matrix is a matrix P. If one of these variables is in state 2, then you have a set of transition probabilities emerging out of that. So associated with each of the arrows here is a whole matrix. And another way to write it is this lattice diagram, where if you're in state 2 at some time, then you have transition probabilities to all the next states at time, the next following time, given by that row of the matrix P. So in particular, if you're in state 2, then that picks out a particular vector of probabilities of transition to all of the k next states. So it's a k-dimensional and I'm drawing it in a way that we're already kind of familiar with these kind of discrete measures. This is not infinite. This is discrete because we have k states. But pretty soon we're going to make it be infinite with our new tool. And so as you proceed through time, you hop from state to state, and you pick out different transition rows of the P matrix as you move around through the state space. Okay, so hopefully that's familiar to you. How many states should we use? This has been a big problem in many, many settings, in particular in our speaker diarization. We don't know the number of speakers a priori, so it really is not at all clear how to set the number of states. In the motion capture, we don't know the number of behaviors a priori, and then you can think of lots of other problems. A lot of these come up in genetics and biology where you don't know the number of entities. Moreover, we have structure to the state space, so we have jumping jacks, and that's a whole kind of an entity that should be shared as an entity. And so there's a structure that classical HMs don't capture. Okay, so I'm going to argue that we can solve these problems in a very clean, elegant way. And the way to do it actually is just to build hierarchies. So we're not actually going to need any new ideas. We're going to use a classical Bayesian idea in the context of completely random measures and Dirichlet processes to do this. Okay, so a little bit of kind of statistical-like math. So at the bottom of a hierarchy is that you have a parameter of some kind. And the data are obtained by some family of distributions indexed by that parameter. Now, where did that parameter come from? Well, it came from some distribution on parameters in the Bayesian story. So in a classical Bayesian story, this might be a Gaussian. So given the Gaussian, you get a parameter, and given the parameter, you get some data. Okay, but we're not doing that. G is not going to be a Gaussian anymore. It's going to be coming from some stochastic process that has its own parameters. There typically are two parameters. There's a concentration parameter and a base measure. So I call this B naught in the previous slides for the completely random measures. And then alpha, this is typically a probability measure. This integrates to 1. So this is the actual integration. If you integrate B naught, you get a number, and that's called alpha. So it's the kind of concentration and then the actual probability measure. Anyway, there's a sum stochastic process which gives you G's. And so you've now seen pictures of what G could look like for these spiky diagrams. And that gives you a bag of parameters. There's a countably infinite number of locations, right, where you can sample. If you sample from G, you get one of those countable atoms. Because everything else is 0. You've got to get one of those atoms. And you get them with probability proportional to the height of the atom. Right? So that gives you a theta, and then from theta you get some data. This is a pretty rich way of generating data. There's a countably infinite number of locations. You get a parameter, and then you get a distribution. All right, so if you actually want to draw this whole thing, maybe I did this on some slide. The thetas are all located at these atoms that are in G. So they're kind of fixed. All right, but then F is a convolution. It convolves around that. Right? So you get a little kind of smudge around theta. OK. Now, to solve the HMM problem, all we have to do, you'll see, is to go not from this classical hierarchy, not using this classical hierarchy. That wouldn't suffice. We have to go to one level up in the hierarchy. So just kind of go through this a little bit. We have data at the bottom. That came from parameters. Parameters came from a random measure. We're now going to need multiple random measures. OK? And so the parameter here, G naught, is itself going to be drawn from a stochastic process. That's got a couple multiple random measures. And just to say concretely why we need multiple random measures, we have multiple rows of our transition matrix. Each one of those is a random measure. So we have multiple random measures. If they weren't coupled in some way, they would not overlap with probability 1. You wouldn't get a single state space. You'd get a bunch of decoupled state spaces. That wouldn't solve your problem. You need one state space for the HMM. All right, so you've got to couple them. And so this construction actually does that. All right, and another way to draw this construction for a specific case of the Dirichlet process is going to be on the following slide, but it may lead up to this. This is the same kind of little thing I had before, except I'm now using the Dirichlet process as a specific example of stochastic process. So you haven't entirely understand what a Dirichlet process is yet. You don't really need to, but the main point is that it comes out looking like one of these objects here, and it integrates to 1. Okay, that's the main point. Okay, so there is an underlying base measure. It basically, if you remember the Poisson process construction on the omega axis, there was a base measure that gives you the location of the atom. So these locations are given by that. And then there was a concentration parameter, which roughly tells you kind of the dispersion. In the gamma process, it's the height of the atoms. But here it's kind of the amount of variance that you have in the atoms. And conditioning on that, we pick a specific parameter that's one of these atoms, and then from that we get a distribution. Maybe with that is, maybe this is a Gaussian distribution, and that's the mean of the Gaussian. All right, so that has a name. That's called a Dirichlet process mixture model. This has been studied going back into the 80s and 70s by statisticians as a model of clustering, where you don't know the number of clusters a priori. And another way to describe this is by integrating out the stochastic process, and you get an object called the Chinese restaurant process. This is kind of a beautiful little preferential attachment dynamics story. And it arises because we have this discrete measure underlying all of this. Okay, so we explain the Chinese restaurant. It's a measure. It's also a stochastic process. It's a stochastic process on partitions. So we have customers coming into a restaurant, and the first customer sits at the first table. This is a Chinese restaurant, so you have round tables. First customer sits here with probability 1. Second customer joins that customer with probability 1/2 and starts a new table of probability 1/2. The general rule is you sit at a table proportional to the number of people already at the table. Okay, so it's a preferential attachment story. All right, so after n people have come in, it's random assignments. You get a random partition of who sits together with who. It turns out to be an exchangeable random partition, i.e., even though we did it in a particular ordering, the distribution you get on partitions is independent of ordering. Okay? It's kind of an important combinatorial fact about this process. You can prove that after n people have come in, there are on order log n occupied tables, and this has a heavy tail, although not a power law tail. So it's preferential attachment, but it falls off at some point faster than a power law. There are generalizations of this that have actual power law tails. All right, so this one that's called the Chinese restaurant process. And a very direct way to use this as a clustering model is what's called the Chinese restaurant process mixture model, if you will. It's not really a standard name, but let's call it that. And so the story here is just that the first person to sit at a table draws a parameter vector for that table, and everybody else who joins at that table inherits that parameter vector. So everybody there has the same parameter. You can call that a cluster. And everybody at a different table has a different parameter vector. That's a different cluster. If the parameter is like the mean and covariance of a Gaussian, you get these kind of ellipsoid-like objects in some space. And the number of clusters grows as log n. As you get more and more data, you get more and more clusters. Slow growth, log n. That's a non-parametric kind of model. The number of parameters, i.e. number of clusters, isn't fixed a priori. It's allowed to grow as you get more and more data. Okay, and so I actually drew some data here. As in the blue are the data points. And as you get more and more data points, you start to get more and more ellipsoids growing at rate log n. So these are Gaussian. The F in this case is Gaussian, and the theta is the mean and covariance matrix of these Gaussians. Okay, just before I go on to that slide, so where do these Chinese restaurants come from? Well, one way is just it's a nice object that a probabilist studied. In fact, it was invented by a probabilist, Lester Dubins at Berkeley, just to study its probability properties. But it turned out that it can be derived from the Dirichlet process. And so here's, I'm going to just give you, in English, the kind of the connection, intuitively. So the Dirichlet process is one of these spiky random measures. And it integrates to 1. So you can think about it as giving you an infinite number of options, and you pick one of them. Okay? Now, it's drawn, underlined that this is the gamma process, which has a bunch of kind of few big spikes and lots of little tiny spikes. All right? So if you come into the restaurant first, not in the restaurant, you come into the Dirichlet process first, and you pick one of those spikes, you'll probably get one of the big spikes. All right? And then I come in after you, I'm probably to get one of the big spikes as well. That means we sit at the same table. If we pick the same spike, we're at the same table. All right? And if we keep going, there are going to be a few highly occupied tables. Those are the big spikes. And the math just works out so that that story is exact. That if you draw from the Dirichlet process and then you sample individuals from that, the allocation of people to spikes is exactly given by the Chinese restaurant process. Okay. All right, so that's a kind of a quick tour through a few new ideas of how to construct interesting distributions on data with infinite numbers of parameters. And then now the new idea we're going to bring to bear on this is, again, hierarchy. So this is useful throughout parametric statistics. In fact, it's probably the main reason to be a Bayesian. Bayesians don't really like priors that much. Priors are a bit of a pain. But they really like to be able to shrink or share information among multiple parts of a model. So in particular, if we have multiple clustering problems, multiple Dirichlet process mixtures, it's often natural, in fact, in our HMM problem, it's required, that we want to share clusters among the multiple clustering problems. Okay. So the way we're going to do that is the following diagram. This is one of the more important diagrams of the talk. So here is an approach to sharing clusters among multiple clustering problems. So it's the same diagram as before, except instead of just having one G, we have multiple Gs, G1, G2, and G3. Now, if each one of those were drawn independently of each other, the locations of the atoms would have no overlap with probability 1. The underlying base measure is absolutely continuous, so you get no overlap with probability 1. If there's no overlap, then you don't have any clusterings between groups. All the groups are completely independent. We need to get some of these clusters here to fall in the same places as they fall over here, because then we tie together everybody in those groups. They're all belonging to the same cluster. All right, how do you do that? Well, the way you can do that is you can say they're resampled from an underlying base measure that's kind of the mother of all atoms. Okay? So this guy is sampled once with a base measure H. And then those atoms this is the base measure which is shipped into the draws of the children Dirichlet processes below that. So this was work that we did at Berkeley a couple of years ago, and this was actually motivated by a genetics problem. The data here were the single nucleotide polymorphism, SNPs. And these were SNPs for different ethnic groups. So you had African, European, and Asian SNPs. So African, Asian, and European. And we didn't know the number of phases or clusterings or haplotypes in our SNP population. So we wanted to use a non-parametric model for that. We wanted the number of haplotypes to grow as you get more and more polymorphisms observed, or more people observed, sorry. So we built Dirichlet processes for each of the different groups. But now we all know that everybody originally came out of Africa, and so some of the haplotypes you see in the Asians also are African haplotypes, and some of the Europeans are African haplotypes. So we wanted to share the haplotypes We didn't want to analyze them all separately. That loses statistical power. We didn't want to group them all together because we had to have a lot more Europeans, and not Europeans would have dominated everybody else. All right? So we needed to analyze them separately but tie them. And that's what this picture was the idea, was that we'd analyze them separately, but they would all have the underlying mother haplotype, which is more or less the African haplotypes. And then everybody else would be perturbations off that. And this really works. This actually is the best way to analyze multiple ethnic group haplotype data. And then we started realizing this is going to be used for lots and lots of other applications, well, sort of concurrently. I'm going to skip this next slide, and I'm trying to, yes. OK, so a couple of slides ago showed a fairly complicated picture, this picture of all this kind of stochastic process machinery. And just like in the case of the Dirichlet process, you could ask, what happens if I integrate out all that machinery? In the Dirichlet process, I got this Chinese restaurant process, which is a nice little simple model to understand. And what happens if I integrate out this machinery in this diagram? Do I get another kind of simple little EARN model or kind of thing that probabilists can study? And you do. It's something we call the Chinese restaurant franchise. Okay, so we're now trying to share things among multiple groups. Say, if you want to think concretely, these ethnic groups. So group number one is the Europeans, the Africans, the Asians. Now we're going to have also a buffet table. And in the buffet table, there are dishes on the buffet table. Right? So someone comes into group 2. So suppose that I'm an Asian, and I come into group 2. And now I sit at a table proportional to the number of people already at the table. There's already people in the restaurant, and I join one of the tables, or I start my own new table. If I start my own new table, what I'm going to do, if I'm first to sit here, then I get to go up to the buffet line. And I pick a dish in the buffet line. Okay, so maybe pasta alla carbonara. Okay, nice Asian dish. And I pick that dish, and I bring it down to my table, and everybody who joins me has to eat the same dish. So there's one dish per table. And also, I put a little check mark next to the carbonara up here. Okay? Now, if you are a European, and you come into the European restaurant, and you sit at a new table, and you go back up to the buffet line, you look at the number of check marks next to all the dishes, and you pick a dish proportional to the number of check marks next to it across all the restaurants. That's how you get the coupling among the restaurants, is the check marks in the buffet line. Right? And then you get coupling within a restaurant by the usual Chinese restaurant dynamics. You sit at a table, depending on how many people are already sitting there. So we get the exact couplings we want. And that's not just a cute metaphor. That's actually the mathematical object you get when you integrate out the hierarchical Dirichlet process. OK, so anyway, hopefully you get the picture, a little bit of the picture here of how you take stochastic processes together, hierarchies, and you can build some models that seem not to be too unrealistic for some real-life problems. So here's another real-life problem we've applied it to more recently. We have a paper that's just been finished on this. So it's been a good, challenging problem for, I've been involved in this for about 5 years, to model the backbones and side chains of proteins. And this is just going to be the backbone part. So a protein is a chain of amino acids. Amino acid has a backbone, which is a alpha carbon, and a nitrogen carbon hanging off of that with a little bit of oxygen. And then hanging off the alpha carbon is the residue, which is a bunch of atoms itself, which tells you which of the 20 amino acids you are. So let's not worry about the residue. That's the side chain for now, or not in this talk at all. And let's just worry about this backbone. So it's kind of like a little robot arm. It's got just a kinematic structure. And there are 2 dihedral angles you need to describe each one amino acid. So there are several atoms here. You just need 2 angles to do it. Those are called psi and phi. And if you plot the psi and phi angles in a 2-dimensional space, across an entire protein or across a bunch of proteins, you get what's called a Ramachandran diagram that describes backbones of proteins. Okay? So one particular point here is one particular amino acid configuration. This is a set of them. And you get regions of the space which are occupied. This is the alpha helix region. This is kind of the beta sheet region. And there are lots of other kind of subclusters. And all these kind of reflect the quantum chemistry. You have hydrogen bonding. There's sort of discrete kind of things that happen because of the quantum chemistry around proteins. And so a lot of these things, quantum chemists can sit down and sort of understand, or a biochemist. But there's lots of kind of little small clusters which are probably not as easy to understand. And so a lot of the problem of protein modeling and then folding has to do with trying to ferret out what all these things mean. So as a statistician, I approach this, and this looks like, wow, that's a Dirichlet process, isn't it? We don't know the number of clusters. We have a few big clusters and a bunch of other small clusters. If you get more and more data, I bet you there'll be even more clusters emerging. I just can't believe there's a fixed number of clusters underlying proteins. And so I really want to apply the Dirichlet process here. Okay? And if you do that, you get a pretty good energy model for proteins. You can put it into protein folding problems, and it's OK. But it's not really as good as it can be. And the right way to do it is to say, well, I don't want to lump all of the proteins together. What I want to do is break these out by what neighborhood I'm in. Because if I know what amino acids on my left and my right, that'll affect the steric property. That'll bend the protein in certain ways. And that has predictable effects on the central angles. So I really want to have different problems for all the different neighborhoods. So I have 20 on the left, 20 on the right. That's 400 different neighborhoods. So I've got 400 clustering problems. Right? But I don't want to treat them completely separately because they have some relationships among them. So I exactly want to use the hierarchical-Dirichlet process. All right, so that's what we did. And there's a long paper on this if any of you are working this topic and are interested. Here's an actual output of it. This is some real data. This is for alanine in the context of serine on the right, proline with arginine on the left. And so you see fewer data points here. It starts to get sparser as you break it down. And then you see these curves, which are our density model that our hierarchical-Dirichlet process induces on the space, a density. And you see some sort of regions where there's kind of little bumps coming up, but there's no data. And you might think that's an error. How could a model be putting a bump there where there's no data? And the point is, it's not an error. There's a bump there because in alanine and some other context, there's probably some data there. And that it comes over as a dish in the Chinese restaurant to say you might expect there to be a little bit of a bump there. Okay? So that's a good thing. And in fact, that's what this model is much, much better than a separated out estimator, which is itself better than lumping everything together. And here's kind of the data that proved that to our biological colleagues. This is no improvement over a lumping everything together. This is all the different 20 amino acids, and here's the amount of improvement in log probability for all the different amino acids, and it's really quite huge. Okay, so this is now, we've shown this is being used in the Rosetta program for protein folding, and it leads to improved folding over the baseline model. Okay, so starting to run a little chunk, 20 minutes, I think, 15, 20. So now finally, let's return to this hidden Markov model problem. So remember, we had a hidden Markov model where we now want to say we don't know the number of states a priori. Cardinality should be random. So back to that picture. That before we had k being fixed, and now we're going to let k be infinite. So before k was fixed, k is now allowed to be open-ended. So now if you land in a certain state, we're going to have a countably infinite number of next states you can go to. So that's one row of this transition matrix, which is now a whole infinite vector gotten by the Dirichlet process. So there's a picture of it up there, pi 2. Now, if you had happened to land in state 3, you'll get a different countably infinite vector on the next states. And again, if those had been drawn independently of each other, they would have no overlap with probability 1. That wouldn't be good. That wouldn't be a HMM. That wouldn't be a state space model. That would be a tree-like thing. And that's not what we want here. Maybe for some other model, we want that, not here. All right, so how do you solve that? Well, you have a hierarchical Dirichlet process where there's kind of a mother transition vector, and then everybody else is a perturbation off of that, and that makes you share all of your atoms. Okay, so here's kind of a picture that suggests how that's being done. There's a mother, this which I call beta up here, and then pi 3, pi 4, et cetera, are all drawn as perturbations off that. They have the atoms in the same locations, and their heights are varying to give you the different kind of dynamical behavior. Okay, so slides are probably going a little bit fast for you to get details, but I hope the main idea is kind of the spirit of what we're doing here. Okay, so we did this. This is back to our. This is actually artificial data, but this is back to our speaker diarization problem. So we did this on some artificial data to see if this really worked when we knew the number of states a priori, and it kind of worked. So here was an actual ground truth. This is time. This is the state space, and there were 3 states here. And so our model discovered that there were 3 states here, 1, 2, 3, but state 3 was split into 2 substates. All right, so it discovered 4 states. And then it hopped back very quickly between those 2 states. And what happened was that state 3 and state 4 just happened to have nearly the same parameter value. And so from the outside world point of view, you're just staying in the same parameter value. So it looks just as good. Okay? If you could imagine this a lot more splitting going on, but the Bayesian kind of procedure doesn't like to have too many parameters. It has a log growth on the prior. It doesn't want to have too many parameters. But still, this is a problem. If we infer there are 4 people in the room and they're related 3, that could be a problem for lots of applications. Anyway, so what do you need to do? We can fix this. And the way you fix it is you just put a little bit of world knowledge in here. We've sort of put no world knowledge in here, but let's put a little bit in, which is that people don't tend to speak for microseconds and then someone else speaks for a microsecond. They speak for a little bit of time. All right, so let's put another parameter in, which is kind of the self-state transition. And let's make that have kind of an informative part that says it tends to last for a few milliseconds at least, or seconds. So we have one additional parameter we call kappa. And kappa is the probability if you're in state I, you stay in state I. And it's a random, it's a parameter, so random from a Bayesian point of view. And it just gives you another degree of freedom here. The red thing before was just some random number, and now it's augmented a little bit by this sticky, we call it a stickiness parameter. So we call this the sticky hierarchical dirichlet process HMM. Okay, okay, and so let's skip the sampling, and let's skip, this just shows that it works on the toy data. Let me now go to the real data. Actually, right, here we go. So there's back to our original problem, speaker diarization. And we implemented this model and compared to the, there's a competition every year. This is standard benchmark data from this competition run by NIST. There's many teams around the world that compete in it. The world's champion has been ICSI, International Computer Science Institute. They have a big system built on hierarchical clustering, and a lot of work has gone into that, and they do pretty well. They get down around 10 to 20% error rate. It's called the diarization error rate. It's roughly, it's what you kind of think. You know, if you get the right person at the right time, that's zero error. Okay. So we implemented our non-sticky version of this, the original model, and we didn't do that well. So the XC is the red. The non-sticky thing is the green. And the blue is the new sticky model. And so you can sort of, that's not a great plot. Let me show you the results in a different way. Here is the actual overall diarization error rate for our sticky procedure. We get down overall over 20 different meetings at that error rate, and there's then the world champion, which is ICSI, which was at 18.37. Of course, these numbers continue. These are two horses. The one horse gets ahead, the other one doesn't. So this is about a year old, and the numbers are now getting down to about 15. So for on most of the meetings, here's the ICSI results. Here's our new thing, and so points above the curve are better for us. So there are two cases which we did really badly, but on many of the cases we did better than ICSI. And those two cases turned out to be just because of slow mixing of the Markov chain. We're using the MCMC to fit this model, and in two of the meetings we had, the thing did not converge in the time we allotted. So here is actually some results from, so this is just a who's speaking when. We discovered there are 4 people in the data. This person talked for a little while, then this person, and so on. And ground truth, if there's an error, there's a red mark in there. You see essentially no red over here. Here's another meeting in which you see a little bit of red, a little bit of errors. But basically on these meetings, which last for 50,000 seconds, I guess, we basically solved the problem. You know, one microphone knowing nothing about the problem. You just put the microphone in the room. We can tell you who's speaking when. Here's a different meeting. Again, we pretty much solved the problem. And then here's a meeting in which these are multiple runs of the Markov chain. You can see it's not mixing because we're getting different results as over iterations of the Markov chain. So meeting 16 is our bête noire. We don't do very well. Let me just skip over the slides. OK. Let me just take I guess I have 10 minutes if that clock is correct. Let me check another. Yeah. Let me just take a breath, because I'm out of breath a little bit, and see if there are any kind of quick questions before I turn into the last. I'm going to talk about sparsity and beta processes a little bit. Yes?
Doesn't the, like that last case you were talking about, doesn't it depend on how you pull the parameters off of the speech waveform? Are you using pitch? Are you using amplitude? How do you, I would think that your parameterization of acoustic signal would play an important role.
Yeah, no, so there's a standardized kind of set of speech features. I know you're a speech person and you would like to spend a lot of time talking about that. Basically, we use the exact same ones that the ICSI people use and basically everyone else uses. And they're sort of modestly sophisticated. They're definitely not sophisticated speech features. You know, sort of capstral stuff with a little bit of pitch. And so one could probably get the number. You know, the ICSI people love working on speech features, and they're kind of world champions at that. And I think they've spent a fair amount of time on that. You definitely don't solve the problem by working hard on that. This is a hard problem. You could probably get error rates, you know, a percentage to it here. But you know, I do believe humans can listen to these meetings and actually do it. And I think that there's reason to keep, you know, doing both the probabilistic modeling as well as the speech feature stuff. But we wanted to show that our sort of simple one graduate student sat down in 2 months and implemented this, can compete in an elegant, simple, statistically sound way with kind of a team of engineers working on this thing for several years from the probability point of view. That was the message here. We didn't want to use special features that sort of gave us a boost in the feature space. That was the point. Yes?
So just a quick comment. It's really interesting for this crowd, I think, because last year we had Alon Orlitsky here as an invited speaker.
Yeah.
And in a very recent meeting with Susan Holmes and a bunch of other statisticians, it was pretty much shown that whatever Turing and Alon did later on in the context of distribution estimation with an unknown alphabet size boils down to Kingman's result.
Yeah.
Because you have exchangeability, you have all the properties that you need for his partition estimator, which relies on, sort of counting the frequency of symbols and then grouping them according to number of times you see a symbol of a certain frequency.
That's right, exactly. So I'm glad you brought that up. There's a really rich literature here, and I'm just one small representative of this. There's 100 people working on this, and a lot of them are people like Percy Diaconis and others who've kind of worked on random partitions and then earned models that come from that. And there's just a beautiful, beautiful web of ideas underlying this. I'm using them as a statistician for inferential purposes, but if you're absolutely right. There's infinite permutations, and they have interesting combinatorial properties, which has probability properties, which
relates very well to information.
And it relates very well to information theory for all the reasons you guys know about. So indeed, I'm glad you brought that up. If you're interested in some of this, I can give some more pointers to literature of all kinds. Going back mostly to the 60s and 70s when it started to flower. And then now it's being picked up for probability modeling purposes like social networks and random graphs, and then information theory and inferential purposes. So it's a great set of ideas. Okay, I do have a few more minutes, and so in some sense what I've been talking about is somewhat classical from the probability point of view. It's just the kind of the Dirichlet process is the core idea. And I want to leave you with this notion that there are these other classes of stochastic processes which have other combinatorial properties, less classical, but I think are actually really interesting and open up a lot of other new opportunities. So let's forget about the Dirichlet process, which gives you this clustering kind of behavior and partitioning and so on, and talk about this other object called the beta process. So there was the kind of the math equation. This is called the Levy measure, to give it a name. But let's kind of try to make this really simple and concrete. So remember how you constructed these complete random processes. You took a rate function, and then you got a Poisson process, and you did this. So the actual rate function of the beta process looks like this. It goes off to, it has a singularity at the origin. It goes off to infinity really quickly. So you get lots and lots of very small atoms, small weights, and a few of them that have non-zero weights. Doesn't integrate to 1. In fact, it integrates to something typically bigger than 1. So the way to think about this is that it really is giving you a countably infinite number of coins. These are numbers between 0 and 1 for the beta distribution. So these are numbers between 0 and 1, and so maybe 0.3, 0.5, 0.7, and then lots of near zeros. So this gives you a bag of coins, countably infinite number of coins. Right? You can toss those coins, all right, and you will get a bunch of 1s and zeros. And you will get a finite number of 1s and a small number of 1s, and then a whole lot of zeros. So you get a sparse representation of an object by sampling from a beta process and then sampling from what we call the Bernoulli process, for obvious reasons. You get now a sparse representation of it. If you now do that again, you hold the beta process fixed, and you resample the Bernoulli process, you'll get another 1-0 vector, and you'll get lots of overlap of the 1s, all right, because some of these guys have high probabilities of reoccurring. Okay? So you'll get kind of a preferential attachment, but now in the space of features, not in the space of clusters. All right, so here's how I've done this now. So here's, I should have had, the colors have gotten switched now. The beta process is this blue object here. That's the cumulative. This is the beta process. So you get a few atoms that are big, and they tend to lead to lots of 1s when you resample 100 times from this Bernoulli process with this as its underlying rate. Okay? So that's a nice little sparse binary matrix. It has exchangeability properties. It turns out the order of the columns and the rows don't matter for the distribution you get on this object. Okay, so it's a Bayesian's version of a sparse representation. It's being used for compressed sensing. There are now some papers on this, by the way. Here are different versions of this matrix. There's 2 parameters to this. There's the concentration parameter and the overall mass parameter. If you tune them, you can get different kind of matrices with different desirable properties. All right. Okay, so before getting to that, let me say a little bit about, okay. So why would you be interested in this piece of mathematics? Well, so the example I like to give of why the Dirichlet process isn't everything. So statisticians will sometimes ask me, well, why do you need this Dirichlet process? It's pretty powerful. Well, think about what Amazon.com does. So if you go to Amazon.com, it clusters you, at least it used to, into one of a certain kind of a book buyer. And then it looks around for other people in your cluster and proposes some books that those people bought, and then you probably buy them. Okay? In the original days, I knew one of the people who worked on this system and when Amazon got started, and they built it as a simple clustering system. They didn't use the tertiary process, but they used another kind of simple kind of heuristic clustering technology. And it worked. People loved it. You know, you found pretty quickly what cluster you belonged to, and Amazon gave you some nice book suggestions. Right? But then that didn't scale. And it doesn't scale for a number of reasons. And one of them is just there's too many different kinds of people in the world. So in particular, I go to Amazon and buy books on Bayesian statistics, well, statistics in general, for example. And I also buy books on punk rock music, because I like punk rock music. And I also buy books, I speak Italian, so I buy some Italian-related things. And I buy books about Berkeley or something. All right, so what cluster am I in? How many people speak Italian, like punk rock, live in Berkeley, and like statistics? Okay, that's just me. Okay, so if you're putting me in the cluster, it just wouldn't work. That's not workable. But instead, if you had a feature representation for me, then it's perfectly natural. I have a 1 for the feature of liking statistics, 1 for Italian, 0 for speaking Arabic, whatever. There's a big sparse vector, and I have a few 1s. And if you have a few of the same 1s, then your book buying patterns can transfer over to me. Another way of thinking about it is that you get the power set now of all the 1s. So I have maybe 4 1s, and you have 4 1s. There are 2 to the 4th possible overlaps we could have just on those 4 1s. So the clusters are really huge relative to the actual representation. OK, so hopefully that convinced you the beta process has got a lot of power. It has combinatorial power that the Dirichlet process doesn't have. What happens if you integrate out the beta process? Do you get the Chinese restaurant process? Well, no. You get another object, and it's called the Indian buffet process. This was discovered by some other people independently of our work. They didn't know about the beta process, but they described a little process on matrices, and we showed later that if you integrate out the beta process, you get this process. And this has a very simple little picture. A person comes into an Indian restaurant now, not a Chinese restaurant, and in the Indian restaurant, there are an infinite number of dishes. They pick a Poisson number of dishes, and eat and sample those. The next person comes in and samples some of the same dishes again, and then they sample a Poisson number of new dishes. And each person keeps coming in, sampling some of the previous dishes, and then a few new dishes, and that fills a binary matrix. That didn't look like it's exchangeable, because it has a kind of a ordering. All right? And they had to show that you had to define equivalence classes of matrices and stuff, and you actually were getting an exchangeable distribution here. But from the beta process point of view, it's obvious. The beta process is completely random. Therefore, any 2 regions in the sample space are independent. Okay? Done. End of proof. You have exchangeability. Anyway, this gives you some nice other intuitions that you have this feature representation. A dish is a feature. So if you and I share a dish, we share a feature. We can eat multiple dishes. We don't have to sit at one table. We eat multiple dishes. Okay. Okay. So there's our little theorem on how beta process leads to the Indian buffet. OK, so I'm now running out of time. I want to skip now to, I think I have, yes, this last little slide on the multiple time series. OK, so you remember our motion capture data. OK, let me just remind myself of, I think that's the last technical slide. Yeah, and I'm going to be done. OK, yeah, basically. OK, so our motion capture data. How do we solve the problem of finding multiple, who does jumping jacks when, and so on? All right, well, let me just say in English how we're going to do this. It's really pretty straightforward. So imagine there's an infinite bag of states. There's the jumping jack state, the squat state, the twisting state, and so on. Infinite bag. And you come into the exercise room, and you're going to pick a certain subset of those states. I'm going to do jumping jacks. I'm going to do squats today. All right? And you come in, and you pick a different subset of the states, and me, and so on. So that's our feature representation, which of the exercise routines we pick. Having picked some of those exercise routines, you now define a hidden Markov model with those states as your substates. So if you picked 4 states out of the big bag of infinite number of states, then you have a 4x4 transition matrix, and that's your description of the time series. Okay? If I pick 2 states out of the bag, I have a 2x2 transition matrix, and I have an HMM for me. So we have a whole bunch of HMMs, 1 for each time series, where the underlying states are got from a bag of states that's like the Indian buffet process. OK, so hopefully you kind of got the flavor. The picture of that as a graphical model is there. That here's the kind of features. You get a few 1s and rest 0s, and that selects out, kind of masks out which states you're going to use in your HMM, and that's kind of the picture. And does this work? Oops. I thought I had a picture on that. The results. Yeah. Yeah, it really worked really well. So we had tried this with some other architectures that this is a hard problem that didn't work at all, and this really nailed the problem. So this is one of the features, and you can see this feature really is a jumping jack feature. It discovered jumping jacks from this data. And here's a twisting kind of one, hip twisting, and here's a kind of a whirling kind of one. You start to get to some places where it breaks the features. These are multiple features, the same features being described as multiple features. So there's a little bit of, again, too many splittings going on. But roughly speaking, I consider this a big success story. This kind of just took in motion capture data, did nothing other than run Bayesian inference in it, and it solved the problem. OK, I'm now basically done. There was a section of the talk which I'm not going to be able to get to on nesting. Instead of hierarchies, we split things. There's a whole now bestiary of restaurants where you have the nested Chinese restaurant. You have a sequence that's a tree. Again, maybe information theoretic context, because trees are so natural, this will be interesting to you. There's a paper we have on my website if you're interested and how you bring trees into this, and we use that for some certain kind of data, and now I'm done. So I hope that you found that interesting, even though probably very far away from what you're used to working on. But a lot of kind of themes. The main theme is really inference. That underlying all of this is that we have data, we condition on that, we want to infer something about what we believe about the world. And in this case, what we believe is not a little parametric model of some kind. It's a growing, organic, non-parametric model that can allocate more and more parameters to your problem. And I think that's the future. I think that statistics will have more and more non-parametrics in it, and Bayesian non-parametrics. There'll always be sort of a mixture of some parametric structure and some non-parametric structure. And then I think if you like mathematics, you'll find this appealing. There's a lot of stochastic process, a lot of combinatorics, and probably even more information theory in it that I'm aware of. I think there's probably lots more, especially with the model selection issues, kind of possible ties there as well. So thanks for your attention. I'm finished.